I'm going to go through the 5.4 quick check. So the first question is asking us to do a balanced equation for the combustion of butane. I've written out the main chemicals, O2, CO2, and H2O. Now we're going to balance. So since I have 4 carbons, I would start by saying I'm going to have 4 CO2s, 10 hydrogens, I'd say 5 H2Os. And if I count up, I have 4 times 2, I have 8 oxygens, 5 times 1, 5 oxygens. So I'm going to have 13 oxygens. And that means on my other side, I'm going to use 13 over 2 O2s. Now, balanced equation, that is fine, but it turns out this is going to be a case where it's really going to be a lot easier for me if I go back and double everything. So I'm going to use 2, 13, 8, and 10. 2, 13, 8, and 10. Okay, so as we work through our problems, we're going to find out that's a lot easier to do. Second little section here, we want to say, well, we're going to get all these equivalent quantities. So the first one's C4H10. So for C4H10, we have to go back and just figure out our molar mass. So for 4 carbons, that's going to be 4 times 12.01, 48.04. For 10 hydrogens, I use 1.01, so 10 times that's 10.10. So my molar mass, 58.14 grams per mole. So my first answer here is 58.14 grams in 1 mole. Now a mole of CO2, how does that relate to a mole of O2? So CO2, O2, 8 CO2s for every 13 O2s. 8, 13. So that's our heart of the problem, just numbers that come from the balanced equation. Molecules per mole, that's a standard thing. That's 6.02 times 10 to the 23 molecules for every mole of anything. Okay, grams of CO2, well, we have to do similar to what we did here. So we know that, for CO2, that's 12.01 plus 2 times oxygen, which is 16. So altogether, that's going to be 44.01 grams for 1 mole. Moles of O2 and moles of C4H10. Okay, we have O2 and C4H10, that's 13 to 2. Liters of CO2 for 1 mole of CO2, that's a standard number, that's 22.4 liters for a mole of any gas at STP. And moles of C4H10 and moles of H2O. Okay, we know it's going to be 2 from our balanced equation, and from the H2O it's 10. So these are conversions, these molar conversions, these are ones we can use in the problems, as well as molar masses and our standard mole facts. Now, we start out how many moles of C4H10 are required to produce 3.55 moles of CO2. So this is our given value, it's got a number, and this is our desired unit, and that's important. So we're going to start off with 3.55 moles of CO2. Now before we go on with this, we want to stop and say, well, what are we really talking about? We're saying we're going to start here with moles of our given, and we're trying to get to moles of our desired, so we're only going to have one conversion factor. We're going to use our mole ratio as a conversion factor. So this is just a 1 conversion factor problem. And if we remember from our balanced equation, for every, 8 moles, let's go back and look. For every 8 moles of CO2, 8 to 2 ratio. So for every 8 moles of CO2, we had to use 2 moles of C4H10. This comes out to 0.8875 moles, because moles of CO2 drop out, moles of C4H10, and I'm going to rewrite that at 0 point, we have 3 significant figures, so I'm going to say 888 moles of C4H10. Next, we're starting what is the volume, so that's our desired, that can be produced when we have 20.8 liters, that's our given, is completely, let's just say completely reacted. So we start off with 20.8 liters of O2, and we're trying to get to CO2. So let's see what we're talking about. We are starting with liters of O2, and we are trying to get to grams of our O2. So we're going to have to go from liters to grams, no, liters to moles of our given, moles of given to moles of desired, and then moles of desired to grams of desired. So we can see that's going to take us 3 steps. Okay, liters. As soon as we see liters, we know that's 22.4 liters for 1 mole of O2. And now we get moles of O2, moles of our desired CO2. So O2 to CO2, we remember from our problems before. That's 13 O2s, 8 CO2s. Now we're trying to get to liters, so we know that 1 mole of CO2 is 22.4 liters of CO2. And now we just do the math, and I get 12.8 liters of CO2. Now to get that, I used up my liters. I got rid of my moles of O2, got moles of CO2. I have liters of CO2. So I multiplied 20.8 times 8 times 22.4 divided by 22.4 divided by 13, 12.8 liters. And the last problem, what is the mass? So that's my desired. That required to produce 4.5 times 10 to the 22 molecules of H2O, so that's my given. So I'm going to start off with this, 4.5 times 10 to the 22 molecules of H2O. Now let's go see where we are. So we're saying molecules and grams. So we're starting with molecules, and we ended up with grams of our desired. So we go molecules to moles, moles to moles, moles to grams. That's going to take 3 conversion factors. So what do I have? Molecules. So I know there is 6.02 times 10 to the 23 molecules of H2O for every 1 mole of H2O. Then my little heart of the problem, moles of H2O. And we're trying to get to moles of C4H10. Now to get those numbers, okay, we have moles of H2O, moles, we need 10 and 2 are the numbers we're going to use. So 2 for the C4H10, 10 for the H2O. And finally, we are trying to get to mass. Mass is grams. So we know for every 1 mole of C4H10, we figured out before that was 58.14 grams of C4H10. Now we just have to multiply 4.50 times 10 to the 22 times 2 times 58.14 divided by 6.02 times 10 to the 23 divided by 10 and divided by 1. And the answer is, I get 0.8692, and that's going to be grams of C4H10. And since I'm working with 3 significant figures, I'm going to make that 0.869 grams C4H10. And that is the 5.4 quick check.